All right, the next talk is given by my co-chair, Nicolle Zellner, who will be talking about lunar impact glasses, small samples, but big science.
Thank you. So along the theme of impacts from the previous speaker, I'll tell you a little bit about my long-term study of lunar impact glasses and what they can tell us about lunar evolution. So these impact glasses are actually formed in melted regolith during impact ejecta. It's not clear what size crater these impact glasses are actually formed in, though we are developing some hypotheses because we've been analyzing them for so long. Glasses are formed both from the via volcanism, so these are the volcanic glasses, and then the impacts from the melted regolith. Here are just a couple of examples. On the left and the right, you can see that they come in both fragments or shards as well as spheres. And both of these kinds of samples have pros and cons and biases attached with them. They are numerous in the Apollo regolith collections. Just a 5-gram sample of regolith can have hundreds of impact glasses and volcanic glasses, depending on the site that you're at. And in the fines, so the size is less than 50 microns or so, they make up almost half of the Apollo regolith. We can analyze the geochemistry on these glasses as well as their formation ages, and so these glasses then tell us about lunar lithologies and the impact flux on the moon, and by proxy then the Earth. So as an example of the variety of impact glasses that we find in the lunar regolith, here's a kind of a messy chart that shows the ratio of refractory elements on, okay, that's a weird kind of pointer, on the y-axis and on the x-axis, so magnesium over aluminum and then calcium over aluminum. These ratios allow us to measure the refractory elements that are not affected by volatilization, and the compositions of these glasses then will most likely reflect the regolith in which they were formed. The triangles, which are a little bit hard to see, are actually the average regolith composition, and then the glasses, which are the circles, are the glasses that were collected at those sites. So you can see that there is a wide variety of impact glass associated with each regolith site. And the glasses that have a composition that is typical of the regolith we call a local glass, and one that is exotic or not typical of the regolith we call an exotic glass. By studying the geochemistries of these glasses, we can learn about regolith transport, we can learn about gardening on the moon, we can learn about subsurface material that is no longer visible, and we can collect information about sites that were not visited by the astronauts or brought to us by the meteorites. Importantly, as was demonstrated by Neil Armstrong, these are very easy grab-and-go samples, and so if you land on the surface of the moon and you don't have much time, you can easily pick up a scoop of regolith, stick it in the sample box, bring it back, and we can learn about almost the entire geology of the moon, as demonstrated by this graph, which is something that Paul Spudis created for one of our abstracts back in 2002. This is a clementine map in geochemical space. So the red colors are the titanium or creepy material, the greens are the mare material, and then the blues are the highland material. And what Paul did here was calculate the aluminum and iron measurements from the clementine data and created a map in ternary space. So the left-hand triangle then is that color map. The middle triangle is actually the clementine map pixelated in ternary space. And on the right-hand triangle, you can actually see the dots that are the Apollo 16 samples, and then the circles, which are the typical compositions at each of the sites. So even in a very, in about 1,000 glasses from Apollo 16, you really get the entire geology of the near side of the moon, thus demonstrating that these regolith samples with the glasses can tell us a lot about the geochemical nature of the surface. We can also study the argon formation ages of these glasses, provided that they have enough potassium in them that then decays into the argon isotopes. And by understanding the argon ages, we can start to fill in the impact flux. This is demonstrated in one of my most favorite examples that we published in 2007, where we were looking at the Apollo 16 site, which is typically an aluminum-rich site, and so a highland site, and so you'll see that down at the bottom of the triangle. We call that local. But we actually found in that local regolith, or in that regolith sample, 4 exotic glasses that all had an age of around 3,700 million years. They were formed in the same compositional terrain at the same time. And so this is evidence of a very large impactor somewhere on the moon that ballistically transported evidence of that impact hundreds of miles to the Apollo 16 site. The compositions then tell you about not only the impacts at your local site, but also impacts at very distant sites. And they come in a variety of sizes as well as shapes, as I mentioned before. So why do we care about the impact flux? It's important to understand what kind of objects are hitting the Earth and when, and so we use the moon as a proxy for understanding that. We have a variety of different impact scenarios here, which I don't think we've all agreed on which one is the appropriate one. The cataclysm, of course, was proposed in the 1970s, and there's been variations on that. If you read Morbidelli's most recent 2018 paper, when they tried to account for the sequestration of highly siderophile elements, they say that they can explain that by reverting back to this monotonic decline or smooth decline. As Bill mentioned, there's a lot of interesting things happening on the Earth, especially during the first billion years of solar system history, including evidence for water and continents at around 4.3 billion years ago, as evidenced in terrestrial zircons. First life appears to be showing up around 3.8 billion years if you believe the carbon isotopic evidence, and then we start to see fossils around 3.6 billion years ago. So understanding that impact flux helps us put into context these biological and geological events. But not all lunar glasses are the same, and so when you are analyzing the ANGSA samples, for example, or grabbing and looking at other lunar glasses from different sites, there is a difference between what the compositions and what the shapes will tell you about those glasses. So we've developed a practice of assigning a qualitative assessment to the lunar glass ages. On the y-axis, you can see the age of the glass, and along the x-axis is the fraction of argon released. And ideally, you would like to have many different steps that all show the same age, and we call that a plateau, so that's demonstrated by the bottom graph, and we call that a good assignment. Other times you don't get a good age on these glasses, and there's some discussion about whether or not 50% or 70% argon released allows you to give that a good age. We decided to call that fair. So by understanding the size and the shape, the compositions of these glasses, we can leave out the bad data and report the good data. One of the things that we tried to do in order to establish some selection criteria is take a look at the argon ages after the fact and figure out what kind of glasses gave us those ages. So these are bivariate density plots that show the size on the y-axis and the composition as a fraction of non-binding oxygens along the x-axis. And basically what this means is if a glass has more iron and titanium in it, it's going to be more likely to retain argon. And what we see here, based on the argon plateau plots, there's a wide variety of sizes and compositions that will give you a poor age, and there's a very narrow region of compositions and sizes that will give you a good age. And so we've constrained the selection criteria then to be glasses that are greater than 200 microns and have an XNBO value of 0.23 or higher. These are going to be the glasses that are going to give you good, reliable argon formation ages. Spheres and shards also have really interesting information to tell us. So the original reports that came out with lunar impact glasses focused mainly on the spheres. This was a report by Culler et al. In 2000. And what we found is that spheres are more likely to be younger in age. And this is just a result of the fact that physics likes spheres, and so when impact ejecta melt into little droplet, or melt, they're going to form droplets first. And the spheres that are collected at the surface then automatically are the younger glasses because they haven't been around on the surface for billions of years to be hacked into shards. So when we look at the distribution of impact glasses with well-constrained argon-argon ages, we find that there's a preponderance of spherules with very young ages, and that spheres are rare at older than about 2 billion years. Shards, on the other hand, perhaps by virtue of their very large size, have been around on the surface for billions of years. And so when we look at the lunar glasses, it may be that the shards are better representative of the impacts that have occurred on the moon over time. Shards are also more likely to be ballistically transported from very far away, so they represent the exotic composition and bigger impacts, whereas spheres are more likely to be formed in very small local events, and so therefore only represent local impacts. We modeled this in 2018. A graduate student at Purdue, Yawei Wang, and the group, David Minton's group, we demonstrated that these samples, these spherules, for example, are more likely to be in the upper few centimeters, and that the preponderance of these spherules in the collection is likely due just to the sampling strategy by Apollo. So as we understand it then, this is the impact flux as represented by lunar glasses. Lunar impact glasses, again, we see kind of this tailing off of impacts older than 3,700 million years. It's not that there weren't impacts older than 3,700 million years, we just haven't been able to see them yet in our impact glasses, so that could be a limitation on those samples. We see a dearth of impacts from about 3,500 million years to about 1.8 billion years, and then we see that dominance of spherules in the last 500 million years or so. We also see some episodic spikes, including one at 800 million years ago that we're trying to reconcile. And I just wanted to point out where Bill Bockett's 2 billion year event might be represented in that flux. So some of the things we want to investigate now are whether or not these impact glasses retain a memory of impact generated magnetism. I'm working with a group at Harvard to understand that. And also what is significant and what is not significant. In the samples that we see, is it a sampling bias or does it really show an infall of asteroidal material in a very narrow time range, or is it just part of the everyday background flux on the moon? Ideally, we'd like to find the source craters for these things. That would require higher resolution orbital data, as well as a better understanding of both major and trace elements. And finally, investigating the solar wind. So one of the projects related to that is looking at some samples that were collected from drive tube 680012. These are the glasses that have been analyzed, and you can see that they have a variety of compositions, including Highland and Mare impact glasses, as well as one volcanic glass that was found in that collection. So we're investigating that. And with that, I'll just leave it here. And for those of you who are planning missions, remember that impact glasses can give you a lot of information about that object, whether it's samples from the moon or samples from another planetary body. Thank you.
Hello? Oh, it does work. So when you specifically mentioned higher resolution orbital data to find the source craters, and so more than just imagery though, right? Are you talking about geochemical data infrared or gamma ray?
I think the compositional data that will allow us to get a better sense of specific areas inside of craters that could be assigned to these glasses. So whatever's done from orbit, I would like to be able to ground truth that with the samples that we have in our collection.
Questions? All right. Thank you very much.
Thank you.